Hello again, Calc 2 students. This is still 10.1, 10.2, kind of blended together. 10.1 was about Taylor polynomials. This is going to be about Taylor series. So we're going to take that next step, and the series that we already had, we're going to, or the polynomials we already had, we had those patterns, we're going to make them infinite series. And so we care about modeling particularly functions that work really well, but also we care about their radius of convergence, right? That's why we did 9.5. We want to know when these are correctly modeled. And so we're going to start by talking about the most important series here and which ones are which. So we did cosine, sine, and e to the x in the last video with charts, and we found patterns, but we didn't find the series formula for these. So if you think about cosine, what we found was we found something like this, right? X squared over 2 factorial, x to the 4th over 4 factorial, this pattern. What we did find was that all of the powers were even, right? So if you look at these down below, this one is the one where I have x to the 2 in. All these powers are even because the 2 makes it so that when n is 0, I get 0, but when n is 1, I get 2, and n is 2, I get 4, and I never have odd numbers. So this one is cosine. And then this next one, sine, was odd, right? We only had odd terms. And that's going to be this one, right? Because these are even numbers and then adding 1. So when n is 0, we'll get 1. When n is 1, we'll get 3, and so on. They're alternating, which these original ones were alternating, right? And then the power matches the factorial on the bottom. Now, 1 over 1 minus x, I'm going to skip real quick, was a geometric series, right? So that's the only one down below that really looks geometric without any factorials. And that makes e to the x the last one, which we could kind of tell just by looking at its series that we created, that you got x to the n over n factorial, right? It was x cubed over 3 factorial and so on. Very simple. Sine and cosine have kind of awkward looking summations, so if you could just memorize the pattern, you can do everything you need to do. E to the x and 1 over 1 minus x are pretty straightforward series, easy to remember, so you might just be good with those. Okay, so what do we want to do next? We want to try to change the center. So for x2, we want to actually have e to the x be centered at 2 instead, and I will show you graphically how this looks different in a separate video where I'm going to talk about 9.5 and the Taylor series using Desmos. But let's go ahead and just try to do this out. So let me show you how the chart is going to be different. So we're going to write it in long form, and then we're going to write it in summation form. I need some space to write this out, so I'm going to get a blank sheet of paper. So we want to do that chart method from before. So we want to figure out, we have n up top, and we'll do 0, 1, 2, 3, and then we'll go ahead and jump to 10 at that point because e to the x is pretty boring. And then we wanted to get the nth derivative at x. The next line was to plug in 0, but not anymore. We're centered at 2, so we want to plug in 2. We still want to divide by n factorial. So it's still e to the x a bunch of times. Now I plug in 2 and I get e squared. So I got 1 each time before, which was kind of nice. Now I get this weird e squared. When I divide by n factorial, nothing happens here, nothing happens here. Now I have 2 on the bottom, and then I have 3 factorial on the bottom, and then I have 10 factorial on the bottom for this. So it's very tempting to just start putting these as coefficients of x. These are coefficients of powers of x minus 2. Remember that the general power series, if it was centered at 0, looked like this. But at A, if you had a different center, it looked like this. And this was for a general power series. Or maybe you had an AN, because for Taylor series we're using AN. But you had this different center here, okay? So we just got our coefficients. We got our sequence AN. But I want to say it's e squared is the constant, and then e squared times x minus 2. And then e squared times x minus 2 squared. And then how far did they want me to go? Just in general. So e squared x minus 2 cubed and so on. Okay? And then they also said write it in summation form. So that's going to be the an is always e squared, and then x minus 2 to the n. I forgot my factorials, didn't I? Excuse me. So 2 factorial here, 3 factorial here. So there's still going to be an n factorial on bottom. And this is going to go in from 0 to infinity, because when it's 0, you'll just have that e squared by itself. So there's the long form. This is still e to the x. It looks different, and graphically I'll show you. This graph and the regular e to the x series will become the same thing eventually. If you go to infinity, you get the same picture. But this one will look really good at 2 to start. The other graph will look really good at 0, but eventually they'll do the same thing. And I will show you that graphically here in a minute. All right, so let's go back to the practice. Let me show you x4. Excuse me, x3. And this one's going to feel a little goofy. I'm going to do what usually students do. This is one of those problems, you know, how I like to include somewhat trick problems in class where I have you do something and then you're kind of like, wait, this is hard. And then you realize that it's easy because it's just weird. So let's do this. We're going to use the chart again to make this Taylor series. So I need the function and its derivatives. I need to plug in 0. We're going to center this around 0. And then we are going to divide by n factorial. So I'm not sure how many terms we need. We'll at least go this far. And so the function is this. The first derivative is 6x plus 5. The next derivative is 6. Every derivative after that is 0, right? So I don't need those. So I should stop drawing extra terms. When I plug in 0, I get 7, then I get 5, then I get 6 because there's no x to plug in. And this is all 0. Divide by n factorial, and the only one that matters is 6 divided by 2 factorial. Gives me 3, right? This is still 7, this is still 5. Okay, so I get 7 plus 5x, because these are coefficients of x, to the n, and so this is x squared. And the thing that you should notice, let's scroll up a bit to what I got here. So when I write that out and I do the coefficients here, what you should notice is that that is the function I started with, just written in the backwards order. Why did that happen? Because I'm trying to model the function with a polynomial. It's already a polynomial. The best polynomial that models a polynomial is itself. So if you have a polynomial, there's no reason to do a Taylor series. This is kind of a trick question, right? So polynomials already are very well modeled by themselves if I need a polynomial model. Okay, so that was a bit of just silliness. Let's go to x to the 4. I think I need to leave you guys some practice here. So I'm not going to do this one. I'm just going to tell you the answer real quick. And this would be good practice for you to do 9.4, 9.5. If you go, sorry, 9.5, radius of convergence. If you look at these 4 series, how do you do radius and interval convergence? You do the ratio test, and you check the endpoints and all the crazy stuff you did before. What you should find is that for cosine x, sine x, e to the x, the radius should be infinite, which is why these are ones we focus on. There's lots of functions we can model, but these work all the time, and so these are our favorite Taylor series. The geometric series, form of 1 minus x, you already know from geometric series or the ratio test, the radius should be 1 and the interval should be minus 1 and 1. Unfortunately, that's a pretty small window where this works, but the geometric series is really intimately connected to, we already saw, to ln, to arctan, to a lot of other series. So because it's so relevant to lots of different functions, we still care, even though it only models in a tiny little space. So these right here, these are the 4 Taylor series you really need to memorize. Not only their formulas, writing their terms out, but also their radius and interval. So you should check yourself, go back to 9.5 and those methods, and do the ratio test and all that stuff to get these. So I'm not going to do that in front of you because we already practiced a bunch in 9.5. I want you to go ahead and do that yourself. And if you don't get the right answer, talk to me on Discord or during an office hour. Okay, x to the 5 is the beginning of what we're going to do in the next lesson, which is we're going to use these 4 functions that we have to model other Taylor series. So we don't want to do the chart every time. We're going to do some shortcuts. So let's look at x5 here. It says use the series for 1 over 1 minus x. They didn't say that, but that's the closest one. Is 1 plus x squared To quickly find a series for 1 over 1 minus 2x, okay, and what's the radius of convergence? Well, what they did was they took x and they changed it to 2x. So every x I should change to 2x. So 1 plus 2x plus 2x squared plus, and it should just be 2x to the n. That's still a geometric series. And so when does this converge? Well, I can do the ratio test, but also because it's geometric, I can cheat a little. This works when 2x now is the r. That should be less than 1. So x should be less than a half. So the radius shrank. This only works from -1/2 to 1/2. Open. And we know it's open because that's how geometric series work, right? They're open on both ends. So that's x5. Okay, x6 and x7 are a little goofy. What you should do is look at x6 and think about just kind of some tricks from up top. You can try to add this up all day in your head or use a formula, but it's not a formula. It's about recognizing which series does that look like. Think about the bottoms here. It's really 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial. That looks like the e to the x series, where that series was 1 plus x squared over 2 factorial. Right, this is e to the x. And it looks like they plugged a number in. And the number it looks like they plugged in was 1, right? So x equals 1. You get this, because all the 1 to the power anything gives you 1, which means this should equal e to the 1, or just e. So this sum of 1 over n factorial, this thing is the sum of 1 over n factorial, equals e, which is crazy. That's another way to define e. That's not how we normally define e, but that is also a sum that adds up to e. Now what about x7? They want you to do the same kind of thing, but they just changed it to alternation. So if you look at e to the x, it looks like they made x minus 1. And so that this would be negative, positive, negative, positive. So the first two terms actually cancel, but they're written out to see the pattern. So that would be e to the minus 1, or 1 over e. All right, the end of this page has a faith discussion about how Taylor series kind of connects everything, and I would love to talk to you about that, but I don't want to just, it's not a discussion if I just talk on here. So we're going to, one of our office hours, we're going to, on Discord or Hangouts or Zoom or whatever we end up using, we'll actually talk about this as a class. So I'm looking forward to that, but I'll stop this video there.